Wave is very important ideal model used in physics apart from particle and a field. There are different types of waves, such as a sound, the visible light, and electromagnetic wave. These waves can be perfectly described by a second-order partial differential equation. Apart from that, there's a wave called matter wave in quantum mechanics, very abstract wave. And to describe that wave, we have applied different ideas. So in this short talk, I'm going to show you the differences between the wave functions used to describe these two types of waves. First, let's consider classical wave. Or wave studied in classical physics. When we study the wave, we start with studying the oscillation. So if the position is oscillated as a function of time, we can use these simple trigonometry functions to describe the periodical motion. This oscillation can propagate in space with or without mediums that will form the wave. How to describe this wave? Then we have to consider the simple equation include two variables. One is the position, another is time. So what we can do, how to describe the propagation of wave? So in the first place, we have to draw that there is, at the beginning, if we consider this wave, the sine wave, and it can be written as the 2 pi divided by wavelength multiply the position. Then we use the phase shift to describe the propagation of this sine profile. So if I draw the diagram, you know what I mean. So if we have the wave propagate in space, and this is the oscillation quantity. It could be displacement, or it could be electrical magnetic field. So this is called phi. And then this is a position in space. So if we use this simple coordinate, we can describe the wave. At the beginning, the wave is just like, let's just draw this diagram here. 1, 2, 3, 4. Yes. So we can see this wave at the beginning, time 0, that will become the sine function. Wave. It's called a sine wave. Okay. You can consider this as a photon taken at a particular moment. So you will see the wave. But after a while, this wave will propagate toward the right direction. Can we use this arrow to describe the direction of travel? We put the P to represent the speed, wave speed. After a while, this wave will propagate along the x positive directions. So as if that these points, each, if you pay attention, that you will see the displacement in space. It's called the delta x. And the time difference is delta t. So the wave speed can be worked out by using the definition of the velocity, that is delta x over delta t. This is very simple mathematical formula to describe the plane wave in space. Of course, gradually we realized if we want to describe much more complicated wave, we have to rewritten this form, wave functions in the complex form. In other words, we have produced I multiply this phase shift. So this is called phase, that would be, can I put it here? It's called the phase, So what is the phase here? I can use, perhaps it's theta here. So theta here is actually equal to this factor. This factor is called the phase. It's called the phase factor. That is 2 pi over lambda, the wavelength, multiply x minus omega t. So in general, the wave function to describe the classical wave can be written as phi x t equal to A is the amplitude of oscillation multiplied E and I multiply bracket 2 pi divided by lambda multiply x and the take away of omega t. Okay. This is wave functions to describe the sound and electromagnetic wave. Then you may ask, what is the underlying equation governing this mathematical form? Then let's do some derivative. Because there are two variables, we have to do partial derivatives first. First, we do partial derivative with respect to the time. So in this case, because a negative sign here, we got a negative I omega and got the phi. Then we do the second derivative with respect to the time. We got the square and eventually got omega square and phi. On the other hand, we can also do the partial derivative with a space variable. In this case, is x. So on the one hand, we got first derivative first. This time, we got a positive I, 2 pi lambda, multiply the phi. Then the second derivative will give us x with respect to x. The second derivative, partial derivative, will give us the I, because I multiply is negative. So we got a 2 pi, we got a negative, we got negative, we got negative 2 pi over lambda square and the wave function. So if you combine the, if you rewrite this function, for example, if we continue rewrite this function as, for example, if you want to rewrite this form, can we just deliberately make the divided lambda here, divided by omega square here, lambda. Then we multiply omega square phi. So in this way, so in this case, we have to use this formula here. We can put the negative sign here. So we can put the negative sign here. We can put the negative sign here. So eventually we have dirt phi, second partial derivative. We're equal to the factor here, that is 2 pi omega multiply wavelength square equal to the second partial derivative with respect to time. Okay, so what is this factor? So we have, for example, in this particular case, if we are studying the electromagnetic wave, we'll use C to represent the speed of wave. It's actually speed of light in this case. We're equal to lambda multiply frequency. Okay. What is the frequencies? The frequencies, if you rewrite this frequency as omega, then you have obliged to divide that by 2 pi omega. Okay. So you can see that this factor is just reciprocal of the speed of wave speed, c in this case, c squared. So if you just simply rearrange this partial equation, we have second derivative, partial derivative, with respect to the x, are equal to 1 over c squared and the partial derivative, second partial derivative, with respect to the time. Then we got a second order differential equation, which is a famous wave equation in classical physics. Remember, this is an underlying partial differential equation for the classical wave. This is a wave function for classical wave. Right? Now let's move to the matter wave. To start with the matter waves, we can still use the general form of wave functions at the beginning. So if we just borrow these wave functions, phi x as function of space variable x and time can be written as the amplitude multiply the e, a complex number I, and that is 2 pi divided by lambda, multiply x, take away of omega t. Of course, both lambda and omega are the wave properties, which is exactly what de Broglie had proposed, that when you consider the matter wave could be associated with electrons. However, in this, when we use wave models, electron is no longer a particle. Rather, it became a wave, the plane wave. So you can imagine this mathematical expression will describe the motion of a single electron in space. However, in quantum mechanics, we have different relation to convert this wave property into energy and momentum. In particular, we have the E equal to h multiply frequency. That is a famous Planck formula for energy formula for photon. We know that this formula can be simply rewritten as h bar multiply omega. So h bar here is simply denote the Planck constant divided by 2 pi. On the other hand, if we use the de Broglie's formula to describe the momentum, then we have h over lambda. Okay, we have the 2 pi over lambda here. So what can we do? So we can rewrite this. We can rewrite 2 pi over lambda as 2 pi, coming to the 2 pi. We multiply the h here, multiply the h here, and divide by h immediately. So we got h lambda. So then we substitute that formula here by introducing the momentum. Therefore, we will got momentum divided by h bar, right? So these are the two constraints or two relations we have to use to describe the matter wave, not electromagnetic wave, not gravitational wave, not the sound waves. Therefore, the wave function can be rewritten as this form, phi x t equal to a, the amplitude, and e expert to the I. Can we replace this by, can we put the h bar outside as well? So we can use I divided by h bar, the cofactors. We have the p multiplied x, take away of energy, multiply the time. So this is the wave function used in quantum mechanics to describe the matter wave. Any particles can be described by this wave function if the particle is freely moved in space at a constant velocity. In the same way, we can also to discover the partial differential equation which can be used to obtain these wave functions. To do so, let's do some partial derivative. First, we can do is partial derivative phi with respect to the time. What we have, we got negative, can you see? We got a negative I e over h bar and multiply the wave function. Okay. Of course, we can rewrite this arrangement. That's what exactly Schrodinger did. So if we arrange this part, we can multiply h bar over here, and also we can multiply another I here. So then we got this slightly different mathematical form equal to the E multiply the phi. Okay, so this is actually part of the Schrodinger equation. Okay, that is part of the Schrodinger equation. It's we're talking about other side. So in this case, we can obtain the Schrodinger equation. It's what we call the Schrodinger equation. It's called a Schrodinger equation. Of course, this is an incomplete Schrodinger equation. At least they provide some idea between the partial derivative with respect of wave function with respect to the time and the energy. Okay. Of course, in general, we have to do, in order to find the Schrodinger equation in its complete form, we have used partial derivative with respect to the space. Okay, can we copy that formula here? For convenience, equal to a exponential I bracket r. We put the, or you can simply use exp, same mathematical expression for exponential function. Then you can use I over h bar bracket. That is a p multiply x and the takeaway of omega times t. I like this more because we can write this exponential function without go to the superscript, without using superscript. Anyway, so let's do the first derivative, partial derivative, this time with respect to space variable x, or the coordinate of particle. First, because it's positive, so we got the I h bar and the rest of this first derivative, just the phi. Simple, right? double check that. I missed out something. We missed the P. We should put the P here because P is, in this case, can be treated as constant. So it multiplies wave functions. Then we can go on for find the second derivative because we're interested to know the relation between the partial derivative with respect to the time and the partial derivative with respect to the coordinate. So the second partial derivative can be obtained, just multiply a factor here, simple. Right, square, we'll put a square here. So in this way, we got this negative, because it's slightly different. We have negative, so basically that will equal to the negative p square and h bar square. Now we have to use some classical formula to convert this p square into kinetic energy. So our argument is that the Hamiltonian in this case is just the kinetic energy, which is can we use EK to in order to use your notation used in high school. That is kinetic energy can be written as half mv squared. Okay. By using definition of momentum, we can jump to the p squared divided by 2m. M represents the mass because momentum is simply the product of the mass and the velocity. So if you compare with these two formulas, you see we almost get the Hamiltonian, except we need the 2m here. So what can we do? So we can, in this case, if we can multiply, before that, if we can multiply h square, if you can multiply h square here, so we got h square, h bar square rather, divided by 2m. Okay. So if you divide if you multiply h bar square, and in the meantime, we also divide by 2m. That would be p square divided by 2m. Do we need to consider the negative sign? Yes, we do. Do we? Yeah, we have negative sign here. Negative p squared divided by 2m. Okay. So from here, you can see that this is exactly the kinetic energy. Or we can actually use Ek, or use a negative Hamiltonian. If we just consider that Hamiltonian is operator for energy. So if you combine these together, so what we have is this simple equation. On the other hand, don't forget that we got the first part of Schrodinger equation. We got E multiplied the phi. So what we can do is that, oh, perhaps I forgot to write the wave function here. That's very important. So here we have to write the wave function, which is phi, So therefore, this part, by do this multiplication, but by do this transformation, we can simply got E multiplied the phi. Okay, this is our equation 2. In the first page, we got equation 1 here. Can you see? E multiply the phi, the wave function. So therefore, these two sides must be equal. These two sides must be equal. So what can we do is that we can put them together. So therefore, we will have negative I omega partial derivative of wave function with respect to the time must be equal to the Hamiltonian. Okay, in this case, is to be exact, is h bar square 2m, and the second derivative, partial derivative with respect to the x, And that, if you consider this operator, that is acted on the wave function. Okay. Just recall the notation of the momentum we discussed before, because the momentum is in quantum mechanics can be written as negative I h bar first derivative x. So we can simply written this as this is so we can see this actually our of the momentum. Okay, I just remind you. So this is actually represent our momentum operator square divided by the 2m, which is exactly the Hamiltonian. So that will be exactly our Hamiltonian operator. In this case, the total energy is represented by the kinetic energy. Okay. So finally, we got the Schrodinger equation. So in this case, we got a Schrodinger equation. So basically, in this particular case, we got a Schrodinger equation, which is that, so we have to, that's why we have to multiply the high h partial derivative with respect to the time were equal to the energy. See, this energy. So that is, if you put the operator here, so we got the partial, we put all fact here, we got what is Hamiltonian? That is, can we use just simply as Hamiltonian? That would be respect to the, that is a function. That is a product of Hamiltonian to the wave functions. Okay. So from here, you can see that if you're looking for the Schrodinger equations, and it will be fundamentally different from the equation of the electromagnetic wave functions. Okay. So if this is a Schrodinger equation, well, I hope that will help you to understand the two different types of wave functions and the wave equations in physics.